I would like to thank the organizers first for inviting me. It's my pleasure to be here for this special occasion. And I would like to wish Eduardo happy coming up in 4 months birthday. I've known Eduardo since he was a graduate student, met him through Vlad, but I think after Vlad's presentation yesterday, there is not much left to add, so I will just wish you many happy returns of the day and much success in all your future endeavors. So let me move on to my talk. So this is the topic that we have been working on for many years. In this talk, I will focus on our most recent results. The experiment actually took several years to complete. And, okay, now it's jammed. Jeez. I promise it was working earlier. Oh, okay. All right, so the key person in that effort was Lily Stanley, who is my former PhD student. And we also collaborated with Ping Lin and Jan Jaroshinsky, and the samples that we measured were all fabricated at IBM. So the key question that we want to address is really one of the most fundamental questions in statistical mechanics. Namely, if you take an isolated quantum many-body system and prepare it far from equilibrium, the question is, does it achieve thermal equilibrium at long times, or does it fail to thermalize, and why? So according to the ergodic hypothesis, different parts of the system will exchange particles and energy, and eventually the system will be able to reach thermal equilibrium, and its properties will be described by equilibrium statistical mechanics. So in this process of thermalization, the information about the initial quantum state is lost with time. Now, in recent years, there has been a lot of interest in systems that do not thermalize. And here is just a partial list of many review articles that have been written on this topic that I think reflect how much work has been put into this field. So in systems that are not able to thermalize, some memory of the initial state is retained at long times, and this is partly, and this is a property that is of interest for quantum information science, which is what partly motivated the interest in this topic. People have been trying to, they have been studying a mechanism to avoid thermalization, and so far the only known robust mechanism to avoid thermalization is many-body localization. This is a mechanism to avoid thermalization in systems that are strongly disordered. And indeed, many-body localization is really an extension of the Anderson localization for single particles in the presence of disorder to an interacting case. So in Anderson localization, particles cannot move, so conductivity is 0, and the system is unable to thermalize. We are talking about isolated systems here. So the question was, can this kind of localization, non-thermalization, survive if we add some interactions? So it turns out that if you add some short-range interactions, it is possible in some cases for this kind of a localization to survive. So the conductivity may remain 0 even up to some finite temperature. So this, in order for this, one of the requirements for this to happen is to have a strong enough disorder. So if a system is in such a many-body localized phase, if you take it far from equilibrium, it cannot, as I said, exchange energy or particles, and it is not able to thermalize. So if the disorder is small or lower than some critical value, the system will thermalize. So this is really a property that reflects the dynamics of the system or the excited states. So a lot of work has been done on this, but there are some key questions that remain open, and these are the questions regarding the stability and the existence of the MBL phase. In particular, it has been shown, again, in some cases, that short-range interactions may lead to the MBL dynamics, and long-range interactions are expected to lead to thermalization, but it is not known precisely how the range of interactions affects the dynamical behavior of the system, and even whether the true MBL phase exists, and especially in higher dimensions. Now I think there is a growing consensus that the true MBL phase may not exist, but there is a so-called MBL-like or pre-thermal regime where even if the system does thermalize eventually on short enough time scales, it will exhibit the dynamics, the true MBL-like dynamics. And importantly, if you want to compare any kind of theory to experiments, in all experimental systems, there is always some small residual coupling of the system to a thermal bath, so that all experimental systems are really in a pre-thermal regime. So there is currently a lot of interest really in understanding the properties of this pre-thermal or MBL-like regime. So in addition to much theoretical work, there has been also a lot of there have been a lot of experiments on various synthetic many-body systems that are shown here. These are nice systems where you can control the disorder and interactions. So they include ultra-cold atoms in optical lattices, trapped ions, superconducting qubits, and spins of NV centers in diamond. So most of this experimental work actually was done on 1D systems, but there is also some work on 2D systems, a couple of papers that I'm aware of. And one of them, or the first one of them, was done on disordered 2D bosonic optical lattice. So this is a system in the absence of disorder. The ground state is a Mott insulator. So they prepare this 2D system, and what they do, to probe the dynamics, you have to take the system out of equilibrium. So they do this quench experiment in which they remove 1/2 of the atoms, say all the atoms that are on the right side. And then they measure the density imbalance with time. In other words, the difference between a number of atoms on the left and the right side. So, okay, so this is what they track, this density imbalance versus time, and they're able to do it for different levels of disorder. So green points show the case when the disorder is 0. You can see this imbalance very quickly goes to 0. So all the atoms are then uniformly distributed. But as they increase the disorder, there is some finite value of the disorder about which the system, at least on these experimental time scales, this balance does not go to 0. So it persists at long times, and this was taken as the evidence for many-body localization. And I just note here that the transition to MBL occurs when all characteristic energy scales in this system are comparable, which is a nightmare for theorists. Okay, so all right, so even in these systems, as I said, they're well isolated, but only up to some time. I don't know, maybe it's a second now. But after that, the system thermalizes or falls apart. The other problem with all of these experiments is that the interpretation of many of them has been complicated by finite size effects. These are not very large systems. And the largest one, maybe, which was the example done for the fermionic lattice, they had a few thousand atoms. And also, similarly, there are many numerical simulations, and they are also plagued by finite size effects. So in order really to make comparisons to theory, it would be nice to have systems, experimental systems, that are much closer to a thermodynamic limit. In particular, we'd like to have some electronic systems. Now, the problem with materials, solid-state materials, is that there is always inevitable coupling of electrons to phonons. So this destroys many-body localization. So the system is coupled to a thermal bath. There was a report on some amorphous indium oxide films of what appeared to be conductivity that vanishes at non-zero temperature, but other interpretations of the data have been proposed. But in any case, what really one needs is a study of the dynamics in an electronic system where usually power law interactions are present, and this is really a case that has been investigated a lot by theorists. So, okay, so what I'm going to show you today are our results, the results of our experiment that was done on a nearly thermally isolated, strongly disordered 2D electron system. We studied the dynamics of the material of the system following a quantum quench. So this is a protocol in which you change one of the parameters of the system quickly, and then you study the time evolution. And Carol yesterday was talking about similar protocols. Okay, so the focus of we focused on the effect of the range of the Coulomb interaction on the dynamics of the system, on the thermalization. In particular, we measure conductivity. And I'm going to tell you what our results are right away. So if you get lost later, hopefully you remember this. So what we found, we did not see any effect of the interaction range on the equilibrium transport, but we did see a striking effect on the dynamics. In particular, we found that in the case of a long-range Coulomb interaction, the system does thermalize, even though the dynamics is glassy because of the frustration in the system. But in the case of a dipolar Coulomb interaction, we find evidence for MBL-like or pre-thermal behavior. So the system that we used is a very old one. This is a 2D electron system in which the first system in which 2D behavior of electrons was established many decades ago. So this is a silicon MOSFET where we have a layer of 2D electrons at the interface of silicon dioxide. So this is a field effect transistor, which means when we apply voltage on the gate, the number of electrons, total electron density in this layer is changed because they're capacitively coupled to this gate. And this is a process that is fast. It's determined by the capacitance of the oxide and the resistance of our 2D layer. And typically in MOSFETs, this is of the order of picoseconds or tens of picoseconds. In our case, for the largest resistance we studied, it's at most 5 nanoseconds. So this is all much smaller than our experimental resolution, which is about 1 or 2 seconds. So this is, for our purposes, this is an instantaneous process. So this is a good system to study because we can change the carrier density easily of over 3 orders of magnitude. It means we can prepare the system far out of equilibrium easily simply by changing the gate voltage. And we can also study thermalization for many different carrier densities across, in particular, across the quantum metal insulator transition. The other requirement, we need this system to be well isolated thermally from the bath, and silicon is wonderful because the Debye temperature is huge, and it has been known to everyone who ever worked with silicon that, you know, at temperatures below a couple of Kelvin, there are basically no phonons. There is no electron. This is why it's more difficult, you know, to cool the electrons at low temperature. So there are no phonons, and the heat transfer from the 2D layer to the rest of the world is by electron diffusion through these contacts, source and drain, and then you have leads that go up to the room temperature because this is all in a cryostat. So you can reduce this coupling to the environment further by placing the samples in leads in vacuum. And this is what we have done, unless I tell you otherwise. Okay, so the system is weakly coupled to BAT. The other thing is we can investigate the effect of the range of the interaction by looking at silicon MOSFETs with different oxide thickness. And it is known that the gate will screen the Coulomb interaction in a 2D layer. And if the mean electron separation, which is the case at low densities, the mean electron separation is larger than, it can be larger than the oxide thickness, then the Coulomb interaction is reduced to a dipolar interaction. Okay, so we have studied samples that have strong disorder, and in silicon MOSFETs, this is due to the sodium ions that are frozen in the oxide. So in this case, again, we are focusing on the case of MOSFETs with strong disorder. And we had two sets of the devices. In one set of the devices, the thickness of the oxide is relatively large, comparable to other MOSFETs that have been studied over the years. So we have a long-range Coulomb interaction. And then we have MOSFETs where the oxide thickness is smaller, so that the Coulomb interaction is dipolar. So I want to emphasize that these two sets of devices were fabricated literally simultaneously. Every single step out of more than 100 steps of fabrication is identical except for the thickness of the oxide. So that any difference between the behavior of these two systems that we see must be due only to the effect of the range of the interaction. And so this screening by the gate is a technique that people have been using for decades in the studies of these systems. Most of the work has focused on studying the effect of screening in the samples with low disorder, relatively clean samples. So we are looking at the case of strong disorder. And in the context of thermalization, there was a study of indium oxide films, which are Anderson insulators. They used, actually, he just CEO at Yahoo, he used this gate to try to, screen the Coulomb interaction, but there was no effect on the equilibration time. I don't know why, but I noticed that, in their case, the screening was not as good as in our case. And also, they had samples immersed in liquid helium, so they were strongly coupled to a thermal bath, in contrast to our case. So for anyone who may be interested, this is just a top view of a silicon chip that has 4 MOSFETs. These are the dimensions of the device's length times width in micrometers. And so first we want to compare the equilibrium behavior of these samples. So this is something we did quite a long time ago in both sets of MOSFETs. So here in each graph we have conductivity as a function of temperature for different carrier densities starting from high to low. So what we see in both cases is that the temperature dependence at high densities is weak, which is something that has been known forever in strongly disordered silicon MOSFETs. And then as we reduce the density, the temperature dependence, temperature dependence is insulating-like. And then at some point we get to the metal insulator transition. And Vlad discussed in his talk yesterday, he showed examples of other materials where the metal insulator transition does not take place, where there is a temperature change in the sign of the temperature dependence, but at much lower densities. So how do we know that we have a metal insulator transition here? Well, okay, I don't have time to show the data in detail, but basically we looked at the temperature dependence at all densities. So here at the lowest densities, we found activated behavior, a characteristic of the, consistent with exponential strong localization. And at densities above, that activated behavior vanishes at these NC, the critical density for the metal insulator transition, and above that, we saw a different kind of temperature dependence, so this is summarized here. Basically, this was our phenomenological result, that we have this metallic, in a sense that at zero temperature, in the zero temperature limit, conductivity is finite, but non-Fermi liquid behavior with an exponent of 3/2. So this is a phenomenological result that actually agrees with one of Lad's papers where they were doing independently. So anyway, so basically what we find then, we have this metal insulator transition at some critical density, which is basically the same in these two types of devices, and then we have this some kind of bad metal regime. So the behavior seems the same, not affected by the range of the Coulomb interaction. We also looked at the scaling around the metal insulator transition, and we found the exponent z nu of 2. In both cases, notably, this value is different from that is found in samples with low disorder and relatively clean 2D samples, which means that this is really in a different universality class, so that in these devices, the metal insulator transition is disorder dominated. Okay, so far the equilibrium transport looks the same, and before I move on to non-equilibrium dynamics, let me just mention what the typical energy scales are. So around the critical density around the metal insulator transition, the Fermi energy and disorder are about 35 Kelvin. In samples with thick oxide, where we have long-range Coulomb interaction, this is the dominant energy. But in the case of screening by the gate, this Coulomb energy is reduced, so all energy scales are comparable, similar to the case of these ultra-cold atoms where they found MBL. Okay, so now I'm going to move on to the non-equilibrium transport, to this quantum quench protocol, and the protocol will be the same for both cases. So you don't have to read this, I'll explain. It's actually a simple protocol. So here, what we do first, we cool the system down to the measurement temperature, in this case 3.3 Kelvin. Okay, and then sometime later, it doesn't matter when, we change the gate voltage. We go from very high density, where nothing interesting happens, we reduce it quickly within our time measurement resolution, within a couple of seconds. We reduce it quickly, and then we don't change it anymore. So the total carrier density decreases very quickly. And then we monitor the evolution of the conductivity with time. So this is shown here at the top. First, I'm discussing this case of the long-range Coulomb interaction. So you can see conductivity drops quickly when we change the total density quickly. But then it takes a really long time, about, I don't know, many hours here, for it to reach some kind of a steady state. And we, at that point, when it seems that it doesn't change anymore, we warm up to some high temperature, cool back down again, and we get the same value. So it seems that we waited long enough here. So you see that this conductivity initially overshoots this final what appears to be equilibrium value, in this case by orders of magnitude. We still don't know why. And then it slowly approaches this, I'll call it equilibrium conductivity. And notice that this is a large perturbation. We are taking a system very far from equilibrium. So this is one example. Now you can repeat the same procedure using the same densities for different temperatures, and you end up with a bunch of curves. So note that here what we are plotting is this ratio, deviation of conductivity from this final equilibrium value for that temperature. So on this logarithmic scale, 0 is the equilibrium conductivity for each of these curves. Okay, so if we fix temperature, as I showed you previously, conductivity decreases, goes even farther away from equilibrium, and then eventually it will reach this equilibrium value. As you reduce the temperature, this process becomes slower. This minimum shifts to longer and longer times. So it turns out that all of these curves, so first we want to see what happens before this minimum, before it starts going back up. And it turns out that all of these curves can be collapsed on the same curve, which is, can be described as a product of a power law and a stretched exponential function. So each of these is a kind of relaxation, non-exponential relaxation that is characteristic of glasses, and it reflects the presence of a broad distribution of relaxation times in the system. And this is a really the same kind of a relaxation that has been observed, for example, in spin glasses above the glass transition temperature as you approach that. So it's very similar. Now we want to take a look at what happens. We want to look at this approach to equilibrium. And it turns out that this is again, they can be all collapsed. It turns out that this is a simple exponential process. We can extract characteristic times for each temperature, and we find that this thermalization time is depends exponentially on temperature, such that in the zero temperature limit, it diverges. So in other words, at any finite temperature, the system in principle will be able to thermalize, even though we can calculate, for example, at 1 Kelvin, this thermalization time exceeds by the age of the universe by a few orders of magnitude. So for all practical purposes, the system is glassy. Okay, and this obviously suggests that the glass transition is at zero temperature. So we have, this was done you know, a long time ago, and we, in addition to this protocol, we also, you know, used other protocols, demonstrated aging, we looked at the fluctuations and so on, and I will not be talking about that. This is all summarized in these book chapters. Here, this is just a same sketch, which shows where we observe this glassy behavior. So the onset of that is here. There is a well-defined density below which observe glassy dynamics, and this is exactly the beginning of this bad metal regime. So we have between an insulator and something else in the regime when KFL is greater than 1, we have this intermediate bad metal glassy phase. And yeah, let me stress that everything that I'm be talking about today happens when KFL is less than 1, when the disorder is strong enough. Okay, so this is the focus of our work. So now we want to see what happens when we reduce the range of the Coulomb interaction. For the case of a dipolar interaction, so we use the same protocol, exactly the same protocol. We cool the system down to measurement temperature, and then at time equals 0, we perform the quench. We reduce the density to a much lower value. Then we do not change it anymore. So you can see that the conductivity drops quickly, and then it increases. The insert is actually a blow-up of this. And you can see again that it takes many hours for the system to reach this, what appears to be equilibrium or some steady value. Again, this is a very large perturbation. And at the end of this process, just like before, so this is the end of that. We warm the system up to some high temperature, cool back down again. We see that we reach the same value. So this tells us that we waited long enough here for the system or conductivity to reach some steady state. Okay, so now let's compare the dynamics in these two cases. So this is another example of what I discussed earlier. This is a case of a long-range interaction for a different density. Again, I'm plotting deviation from the equilibrium value, which is shown by this dashed line at the top for each of the curves. So this is what we found earlier, that this approach to equilibrium depends exponentially on temperature. Now let's compare this to the short-range case for basically more or less the same electron density. So we can see immediately, I think, that qualitatively these curves look very different. Notably, initially at intermediate times, there is negligible relaxation. We have noise, but there is negligible relaxation. We do not see any evidence here of glassing. It's like here where we could fit this to a power law or stretch exponential. And the other really striking difference is that this thermalization time seems to be the same for all temperatures and densities. So that's very strange. And the other thing, okay, so the next thing I want to show is, that this becomes these deviations from the equilibrium, or these effects become observable again when KFL is less than 1. And here are a couple of examples of the data. So here, this is a result of the protocol performed for densities, higher densities. We do not see anything. And then we reduce the density when KFL is of the order of 1. We start seeing some deviations. Then we start approaching, we are still on the metallic side, but we are approaching the metal insulator transition. We see behavior similar to what I showed on the previous slide. Negligible relaxation initially, or at intermediate times, and then basically the same equilibration time. As you get close to the metal insulator transition, the noise becomes huge. Yes, yes, exactly, yeah. Well, you know, for longer range interaction should smooth things out. And I think, yeah, it's expected to have a bigger noise in the shorter, but you're right, yes. So, and especially when we get to the metal insulator transition, you know, this is huge and strange. And, well, maybe not strange, but, you know, we still need to study the noise in this case. On the insulating side, again, the noise is big. It really depends, you know, this depends on the density. This could be here or there or just noisy. So in the insulating regime, again, we don't see any really relaxation, but it's really dominated by the noise at low temperatures. So in order to try to extract some kind of density dependence, something quantitative out of this, we kind of said, okay, let's fix the temperature and let's look at the deviations, initial deviations from this equilibrium value. So this is what's plotted here. Basically, at 10 seconds, the deviation from the equilibrium value as a function of density at temperature about 200 millikelvin. And we see that as, you know, we reduce the density, this grows, and it's non-monotonic. It's really most pronounced just above the metal insulator transition. So this is another property of all these systems that, you know, reflects the presence of an underlying metal insulator transition. Okay, so since this is complicated, now we wanted to, and thermalization time is confusing, it was, because it was not anymore, I think, because it was different from this long-range case. We wanted to focus first on this thermalization time. And again, we looked at the approach to this stationary state or equilibrium value, and we could fit these curves with a simple exponential function, extract this time, and we do it for different densities and temperature, and this is what we get. Okay, we do not see, the time is long, it's like 10,000 seconds, but there is no systematic dependence on temperature or density or sample size or anything like that. So the question is then, what is the origin of this very slow dynamics that we observe here? So since it's not glassy, the other possibility is that, well, maybe it could be many-body localization. Now we know that many-body localization is extremely susceptible to a coupling to a thermal bath. Okay, so far what I showed you, this was done with samples and leads placed in vacuum. But we can also and we did repeat some of these measurements at the same temperature, all the conditions the same, but the samples were placed in helium vapor. Okay, so what we found is the following. So these are the results, some of the results that I just showed you, and here, this is what we found by repeating the experiment with with increased thermal coupling to the bath. And we see that this thermalization time is reduced by an order of magnitude, which is precisely what you expect in the case of a many-body localization. So, excuse me? Oh, okay, well, I think it should work. Okay, so basically what I just showed you here. These are measurements at temperatures where electron-phonon coupling is basically non-existent. And so the first measurement was done with samples in vacuum. So we have weak thermal coupling to the environment. We have this large thermalization time. We increase the coupling to the environment. This dropped by an order of magnitude. Now, if you go to higher temperature, here phonons become important. We have strong coupling to the environment, and we also performed some experiments, and we got the upper bound for the thermalization time to be, this is supposed to be sigma, to be 200 seconds. So this was reduced by another order of magnitude, and this did not depend on where we place the sample, vacuum or liquid helium, and this makes sense because the dominant coupling is really to the phonons. Okay, so what we found is then basically an exponential dependence of thermalization time on the strength of the coupling strength, which is exactly what you expect in NBL-like dynamics. And in contrast, in the glassy case, in the case of long-range cooling interactions, we obtained the same results at temperatures up to 6, 7 Kelvin. There was really no difference. So this glassy dynamics is insensitive to thermal coupling to the environment, which is exactly what one expects. And in fact, it is this sensitivity to the coupling to thermal bath that has been suggested to be used as a key experimental signature or a way to distinguish between glassy and NBL-like dynamics. Okay, so this is what we have found. In the long-range case, we have the system thermalizes, but the dynamics is glassy because the system is frustrated. We have disorder, we have long-range cooling interaction. In the dipolar case, the dynamics seems to be consistent with the pre-thermal of NBL or NBL-like behavior. Now, what about theory? Those papers are not easy to read. Okay, so basically, there are many papers that have studied the thermalization in case of power law interactions, where we have this exponent alpha. And I think they all agree that when alpha is smaller than the dimensionality of the system will thermalize, and this is what we found. And now this case here is a subject of debate. So some people say system should thermalize, others it should not, but many of those studies, and here there are really many more papers that should be included here. Many of these studies really involve numerical simulations, and they have, again, there are issues with finite size effects. So our results is consistent with those that claim that in this case the system can be in the NBL regime. So basically I showed you that in strongly disordered 2D electron systems, when KFL is less than 1, we always observe slow dynamics. In the case of long-range interaction, the dynamics is glassy. Now, this study was actually, we started it many years ago, and the original question that motivated our work was whether glassy dynamics can persist when you screen the cooling interaction. So we have our answer here. No, it does not persist, at least not in the case of a dipolar interaction. But instead, we found a new solid-state platform for studies of thermalization, NBL-like dynamics. And again, this is a system that's much closer to thermodynamic limits than those synthetic quantum many-body systems. And finally, let me just remind you that this study was done in a system that silicon MOSFET that forms the basic building block of modern electronics. Yesterday, you saw some beautiful images of modern silicon technology, but this is really all based on this one single device. So it is, for me, fun to speculate whether these dynamical properties could be integrated with, standard solid-state electronics to form new building blocks for quantum information science. And I thank you very much.
Thank you, Dragana. And now we have time for a couple of questions. So here is.
Yeah, this is a very naive question, but before even talking about the dynamical effects, when you were in the insulating phase, could you distinguish, was there a different resistance as a function of temperature in the insulating side, with or without gates?
Well, there are always gates. In a silicon MOSFET, you always have a gate. You must have a gate.
Without, what I mean is with the one on-screen Coulomb interaction and the screen.
Was there a difference?
Yeah.
Okay, with the screen Coulomb interaction, we found 2D Mott variable range hopping. And without screening, it was more like just activated. But we are relatively close to the metal insulated transition. But this is what, people have been finding, yeah. So I don't know, yeah.
Other questions?
So the systems are two-dimensional, right?
Yes.
Is it possible to extend the study to a kind of a quantum wire if you etch?
If you give me a quantum wire, I can do that.
Yeah, because, well, it's just because of the issue of dimensionality.
Yeah, well, right. So yes, initial, I think theoretical studies, people agreed, yes, MBL exists in 1D, but, for larger, higher dimensions, it's questionable, but now apparently may not even exist in 1D. But I think just like glassiness, this is a philosophical question, right? Whether at infinitely long times it's a true MBL or a true glass, or, for all practical purposes. So, yeah, I don't know. Does this answer the question?
Yeah.
Anyone else? Oh, here is Wei.
I was very intrigued by the comparison you have when you have comparing the one without disorder versus with disorder, the quenching process. There's a very big dip in the transport before you introduce disorder, but then it becomes much weaker.
No, there is always disorder.
I'm confused. If you go back to the very beginning, when you see the first time you quench the system, like maybe the 10 slides or something, like very early.
This? Or no?
No, very early on, there is this, when you quench first, there
the
is
protocol.
a big, this one versus the previous version.
This is the same as before.
But this is very tiny difference, right? But in the previous 2 slides or so, there is a much bigger effect.
Because I think this density is much bigger, much higher than the one that I showed you earlier. But let's see, do I have another one? You may be right. We haven't looked at that in detail. We haven't compared them. No, I don't have that here. I understand. The first, there was a drop by like a couple of orders of magnitude. Yes.
Is that understood?
No, it isn't. No. I've been asking people for the last, 15 years. There are models that can produce overshoots, and this is seen in nature. It's seen by in many systems that are far from equilibrium. But I don't know if there is a universal explanation.
In that first example, it was really big.
Yes, but okay, right, it's here. Let's see. So maybe, I'm not sure, maybe because this density in this example is much closer to metal insulated transition, but you may be right that in general here it was bigger. Yeah.
But no understanding so far.
No. Again, it is possible, it is seen in nature, it exists in some theoretical models, but there is no model that is relevant to this, or that people have demonstrated is relevant for this.
A final question, Thomas.
So Dragana, based on these initial arguments, comparing the two cases, I would have expected an enormous quantitative difference in the time it takes to relax between the case with Coulomb interaction, which, based on the arguments, should have been much faster. But if I look, unless I misread the graphs, the overall times that of your experiments show that it looks roughly the same, right? It's 10 to the 5 seconds for both cases.
Okay, so this time depends on the thermal coupling to the environment. So it can be, 1,000 in the short-range case. It can be much smaller.
Let's switch this off, right? So without the thermal coupling, it's 10 to the 4.
Yeah,
But this was about the same as it was for the Coulomb interaction.
well,
case,
it has to be, okay? It has to be because there must be a temperature where they are equal, because in the long-range case, you have this exponential dependence of this equilibration time on temperature. So, and this one does not depend on temperature, but it depends on thermal coupling. It's constant. Let's say for a given thermal coupling, it's constant. The other one depends on temperature exponential. So there has to be a temperature where they're comparable.
Right, but of course, that would also imply that there is a regime where the MBL like case is actually faster than the glassy one, which is a little counterintuitive.
Again, this depends on thermal coupling. Our thermal coupling is finite, and it seems to, the equilibration time seems to depend exponentially on this thermal coupling. If we could reduce it to 0, it would be exponential. Yeah.
Okay, thank you very much, Dragana. And now